Eaton just reported a 48% backlog growth in its electrical division for the first quarter of 2026. And while Wall Street celebrated a routine earnings beat, anyone trying to actually build an artificial intelligence data center just heard a massive warning siren. We are currently watching the absolute limits of physical infrastructure collide with the limitless ambition of artificial intelligence, and the implications are staggering. If your project is scheduled to energize in 2026 or 2027 and your power equipment hasn't been locked down and engaged yet, you are already late. You are not going to hit your timeline. The market has completely shifted. Project developers, municipalities, and healthcare systems are no longer just competing on budget or real estate. They are now in a desperate zero-sum competition for finite manufacturing capacity. We are talking about the physical bottlenecks of the modern world: switchgear, uninterruptible power supply systems, power distribution units, and transformers. To understand the gravity of this, we need to step back and look at what is actually happening in the supply chain for electrical infrastructure, because it represents a fundamental shift in how the global economy builds the future. For the past few decades, when we talked about technological advancement, we talked about software, we talked about code, algorithms, and cloud computing. The physical hardware, the servers, the cooling fans, the electrical substations, was treated almost as a utility. It was assumed to be there. Before the AI infrastructure demand truly accelerated, the supply chains for large electrical equipment were already under severe pressure. In the immediate aftermath of the pandemic, delivery times for critical IT hardware like servers and routers ballooned to 52 weeks. But the industry adapted. However, the bottleneck has now migrated from the server rack to the substation. According to recent supply chain data, lead times for large power transformers, which used to be roughly 24 to 30 months, have now stretched anywhere from 3 to 5 years. Some distribution transformer lead times have hit 50 weeks, up from 12 weeks before the pandemic. These are the massive, heavy pieces of equipment required to take high-voltage power from the grid and step it down safely so that it can be distributed inside a hyperscale facility. You cannot build a data center without them, and you cannot substitute them with software. This is exactly why Eaton's first quarter 2026 results are the most important economic indicator you might not be paying attention to. In May 2026, Eaton announced revenue of $7.5 billion, a 17% increase. But the staggering figure was that total backlog in their Electrical Americas segment surged 44% year over year. The 12-month rolling average of orders in that segment grew 42% organically. This is not normal growth. This is the sound of an entire industry frantically trying to hoard electrical capacity. When a company like Eaton says their electrical backlog is growing by almost 50%, they are telling you that demand has so radically outstripped supply that the queue for equipment is stretching into the horizon. And this isn't just about raw power distribution anymore. It is about deep structural integration with the very companies defining the AI era. Consider the technical breakdown of what is required to keep a modern AI factory running. Artificial intelligence models, specifically large language models training on massive GPU clusters, require an astronomical amount of electricity. This power generates an immense amount of heat. Traditional data centers relied on ambient air cooling, essentially giant air conditioners blowing cold air through the server racks. But the thermal density of next-generation chips, like NVIDIA's Blackwell and Rubin architectures, has rendered air cooling obsolete. You cannot blow enough cold air over these chips to keep them from melting. You need liquid. Specifically, you need direct-to-chip liquid cooling or two-phase immersion cooling. This technical reality explains Eaton's aggressive moves in the market. In late 2025 and closing in 2026, Eaton signed a $9.5 billion agreement to acquire Boyd Thermal. Boyd Thermal is a titan in highly engineered liquid cooling technology. They forecasted $1.7 billion in sales for 2026, with $1.5 billion of that coming strictly from liquid cooling. By acquiring Boyd, Eaton didn't just buy a cooling company. They bought the missing piece to control the entire thermal and electrical ecosystem of an AI data center.
This leads us to the strategic shift from fragmented vendor relationships to what is now an integrated ecosystem conversation. Eaton also announced a deeper integration into AI infrastructure through a platform called Beam Rubin DSX, developed alongside NVIDIA. This integration is crucial. NVIDIA is undeniably the standard for AI compute infrastructure. By integrating grid-to-chip power solutions directly into NVIDIA's Vera Rubin DSX AI factory reference design, Eaton is positioning itself deep inside the very architecture that supports these environments. They are offering an end-to-end standard implementation, from the grid infrastructure outside the building, through the power distribution units, all the way down to the advanced liquid cooling circulating at the chip level. It is becoming a single, pre-engineered ecosystem.
This compresses the build-out timeline. Instead of a developer trying to piece together a puzzle of transformers from one vendor, switchgear from another, and cooling from a third while waiting 3 years for each to arrive, they are moving toward a unified grid-to-chip model. But the existence of these integrated platforms does not solve the physical shortage of raw materials and manufacturing slots. The demand for these components is coming from multiple, massive sectors simultaneously. The AI data center boom is just one vector. The electric vehicle rollout, the integration of renewable energy sources like wind and solar onto the grid, and the desperate need to replace America's aging legacy grid infrastructure are all competing for the exact same finite manufacturing capacity. They all need grain-oriented electrical steel. They all need copper windings. U.S. utilities and data center operators are literally outbidding each other for transformers. To illustrate this desperation, consider that Crusoe Energy, the company building a massive 1.2 gigawatt data center campus in Texas for OpenAI, has reportedly resorted to refurbishing old transformers from shuttered power plants just as a stopgap measure because new ones are simply not available. We are seeing a massive surge in refurbished equipment procurement because a remanufactured transformer might take 4 to 6 weeks to deliver compared to 50 weeks for a new one. The cultural and economic impact of this bottleneck cannot be overstated. We are moving into an era where securing physical power infrastructure is the absolute definitive competitive advantage. It doesn't matter how brilliant your AI model is or how much venture capital you have raised if you cannot plug your servers in. Analysts estimate that global data center power demand will nearly triple between 2025 and 2030, requiring an estimated $7 trillion in capital expenditure. But money cannot instantly build specialized manufacturing facilities. The U.S. transformer manufacturing base shrank for decades as production moved overseas. Today, China controls roughly 60% of global transformer manufacturing capacity. The U.S. imported over 8,000 high-power transformers from China in the first 10 months of 2025, up from fewer than 1,500 in all of 2022. This reliance on overseas manufacturing for critical national infrastructure creates massive geopolitical vulnerabilities and complex trade policy debates. Tariffs and export controls are reshaping the semiconductor supply chain, but the power infrastructure supply chain remains dangerously exposed. This dynamic introduces significant nuance and controversy into the AI narrative. On one hand, you have technology companies promising that AI will solve everything from climate change to disease. On the other hand, the physical footprint required to build this intelligence is putting unprecedented strain on local utilities and global supply chains.
According to an April 2026 Bloomberg report, more than half of the U.S. data centers planned for this year are expected to be delayed or canceled entirely due to these equipment shortages. Out of 12 to 16 gigawatts of planned capacity, only about a third is actually under construction. The tech giants, Alphabet, Amazon, Meta, and Microsoft, have guided for over $650 billion in AI infrastructure capital expenditures for 2026.
Yet that money is effectively stuck in traffic, waiting for physical switchgear and transformers. So what does this mean for the average observer, the local government planner, or the hospital administrator planning a new wing? The larger takeaway is profoundly simple, but highly disruptive. If you are an owner, a real estate developer, a healthcare system, or a municipality, and you are waiting until the construction phase begins to start thinking about your power infrastructure, you are already entirely behind schedule. You have lost the race before the starting gun even fired. The companies and institutions that are engaging early, years in advance on electrical infrastructure planning, are the ones who will secure capacity. They understand that we are no longer in a just-in-time economy when it comes to power. We are in a queue-based economy. The timeline of human progress over the next decade will not be dictated by the speed of software development. It will be dictated by the speed at which we can bend steel, mine copper, and build transformers. We have to recognize that the digital world is fundamentally anchored to the physical one. The cloud is not ethereal, it is made of copper, steel, silicon, and billions of gallons of water. When an industrial giant like Eaton reports a 48% jump in electrical backlog and spends nearly $10 billion to acquire a liquid cooling company, they are mapping out the exact coordinates of the next great industrial bottleneck. They are showing us that the future of computing requires a profound integrated co-design of power, cooling, and processing. The ecosystem is the product. The grid-to-chip architecture is the only way forward. If you found this analysis helpful in understanding the hidden physical realities behind the AI boom, please send this episode to a colleague or friend who needs to hear it.